Good morning, everybody. We will continue this discussion on the derivation of effective equations for suspensions. So yesterday I gave you an idea about, a formal derivation of Vlasov-Navier-Stokes type equations starting from, let's say, microscopic description. And as I said, there are always, often there are some, let's say, two steps. The first step will be somehow to fix the motion of the particles, so we freeze the position of the particles, and we try to pass in the limit in the fluid equation. And then we look at what happens for the dynamics of the particles. So today I will focus on this first part. So basically, we will consider a fluid equation with fixed positions of the particles and try to pass in the limit in this fluid equation, which is written on a domain which is perforated. So this second part will deal with, I will try to speak about homogenization, even if it's a quite large topic. I will try to give you some insight. So homogenization of, let's say, Navier-Stokes, Navier between parentheses, because sometimes we'll just skip forget about the inertial effects of the fluid. So homogenization of Navier-Stokes on a perforated domain. And there are lots of things to say, but I would try first to focus on the derivation of the Brinkman term. So the one that I showed to you yesterday, of Brinkman type force or term. What I wanted to do for this part is to give you somehow an overview of the literature. It will be something far from being exhaustive because this has attracted a lot of attention. So I will start to tell you what has been done in the early 90s. This has attracted some attention already in the 70s. So we'll try to speak about these first results, and then I will switch to slides for to give you more results, because otherwise it will be too long on the blackboard. And so I hope this part will not be too heavy and too long. But then I would like to give you a proof in a simple setting for the derivation of the Brinkman term. So let's say overview. Historical overview of the literature. So the first result, at my knowledge at least, goes back to 1974 by Marchenko and Huslov. In 1974. So I have to say that I didn't have the opportunity to read this paper since it's in Russian, but I tried to gather some information about what has been done in this paper according to some other papers who speak about this one. So they consider a domain which is bounded, so omega bounded, in 2 and 3 dimensions. And they consider the case where the particles are periodically distributed. So this means that you have a distribution of identical obstacles in your domain. And I don't think that they were spherical, so they just put some obstacle, let's say something like this, which is the same in each cell. So the length of the cell is denoted by epsilon, and the diameter of the obstacle, so let's say T epsilon is the obstacle of the diameter R epsilon, which depends on epsilon. And the diameter is really small compared to the length here of the periodic cell. And so they focus on a Stokes equation on this domain. Let me write this. So I guess that's, yes, that should be. So we give ourselves a Stokes equation with some right-hand side, divergence-free condition. So I will call this domain, so omega, the fluid lives in the domain which is omega minus the union of the obstacles. So maybe I will call them Ti epsilon. Okay. So the fluid lives in omega epsilon, and they assume omega epsilon to be 0 on both the boundary of the particles and the boundary of the domain. So this means that the particles have 0 velocity, so they are not moving. Okay. So actually, you can show that such a quantity is well defined and is H1 0 of omega epsilon. You can also extend it to 0 inside the particles. So I will call U bar epsilon, U epsilon in omega epsilon, and 0 in the union of the balls, Ti over R. So such a quantity is well defined also, I mean, by continuity of the, and it's divergence free in the whole space, in omega. And so what they prove is that U bar epsilon converges weakly to some quantity which solves the following equation. Divergence U and U equals 0 on. And this is the corresponding Brinkman term, which writes like this: since the particles are vanishing, you don't have the dependence on the particles' motion. But let me make precise what is M. So M is a matrix, and it's given in terms of the Stokes capacity, which corresponds to the following quantity. So you solve somehow a Stokes problem on not the cell, but just, let's say, a ball which contains the particle. So here, this is epsilon over 4, and this is the obstacle. So let's say my obstacle is centered in 0. So UI solves this equation. On the boundary of the obstacle and 0 on the boundary So this is on the ball minus the obstacle, which is this one centered in 0, let's say. And EI here are just the elements of the canonical basis in 3 dimensions. So this holds in 3 dimensions. And this is basically, I mean, this is the entry of the ith line and the jth column of the matrix M. And somehow this is reminiscent of what we saw yesterday, because actually if you do a rescaling here, you can always go back to something which is defined on an obstacle of diameter 1. I mean, if you divide everything by the radius, or the diameter r, epsilon, you can see that this quantity scales like r over epsilon to the 3, because ui, you can write it like, let me not make some mistake. Yes, it should be a solution. So what I will call UI1 is the very same problem which takes place over the rescaled ball, where you divide by r epsilon here. So you divide by r epsilon so that this becomes something of diameter 1. And when you do such a rescaling here, you will make appear one radius, because you will get r to the power 3 coming from the change of variable, but then you have 1 over r, which will pop out from the gradient. And so what they show is that actually, I mean, you expect this matrix to be of order 1 if this guy is of order 1. So M is of order 1 if r epsilon over epsilon to the power 3 goes to, is of order 1, I mean, goes to some constants. Whereas this will be useful later on, I mean, to compare with other results. So this tells you that if this quantity goes to 0, meaning that the particles are really too small, you can see that this guy will go, I mean, yeah, you will just recover here m equals 0 somehow. Which tells you basically that your particles are too small so that they have no effect on the limit system. So the idea to prove such a result, I mean, the main ingredients were already there in this paper, so somehow you need to, so basically once you know that u bar epsilon is uniformly bounded, you would like, I mean, you know that it has some limit up to a subsequence, and the main, I mean, the main difficulty is to derive the limit equation. But how do you do that? The idea is to use somehow the weak formulation of the macroscopic model. So, because, I mean, you can write that this would be the limit of such a thing when you're on omega. And so you would like to use the weak formulation for u epsilon or u bar epsilon, which is the extension of u epsilon. But here phi is just a test function which lives on omega, so it does not match the weak formulation for the microscopic model, for which you need some test function which vanish on the boundary of the particles. So the main idea is somehow to correct the test function in order to fit the weak formulation of the microscopic system. And this has been done through some restriction operators. So they construct some operators which will go, let's say, from H10 of, sorry, where did I? Yes, sorry. So from H10 of omega, you would like to to restrict it to something which lives in h10 of omega epsilon, such that if, let's say, you take a test function which is in the right space here, such that it's divergence-free, you would like also that its restriction is divergence-free, so that it's a good test function for the microscopic, and so it already satisfies being zero, right, on the particles. And also, if V is already in the right space, I mean, then you have nothing to do. The restriction is itself. And so the idea to construct such things is to use basically these specific solutions. So more generally, this is somehow referred to as correctors. I mean, you try to correct the test function that you have. And this is basically somehow the main idea that will always be used in most of let's say, a big majority of the works that have been done. So what I would like also, so I will just give you now some other results which are already, before 2000s, I mean, there has been a lot of other results. So one of the most important ones then is the work by Tartar in 1980, I think, yes, which deals with the case of, I mean, this is quite different. I mean, this does not concern the derivation of the Brinkman term, but rather the Darcy regime. But actually, the construction is similar. So this is for the Darcy regime, which means that in the case of periodic distribution of particles, like in this setting, corresponds basically to ask for this quantity to go to plus infinity, which is a reminiscence of the permeability somehow. So in this case, I mean, you have somehow a porous media, so that's what you get in the limit will be rather a Darcy regime. So if you imagine this guy to go to infinity, you can, I mean, this matrix here, so you just inverse and you get U in terms of F and the gradient of a pressure, which is the Darcy, Darcy model. And so so it's more general. I mean, if you ask just this, I think in their setting they just consider this case, sorry, which enters in the framework of what I have written before, but they just consider this setting. And so the tools are always the same. I mean, you need somehow some extension operator and some correctors. And I will try to make this more precise later on. So what I also wanted to say, let me... there is also another famous paper in the 19th, which is the one by Suranescu and Murat, which is the derivation of this strange term coming from nowhere. And this paper is rather dealing with a Laplace version of what we are looking at today, but mainly, I mean, again, is the same trick, the same. The same ingredients are already there also, so Suranescu. This is in 1982. So this deals again with so almost all these are always in periodic distribution of particles. But this is the case of Laplacian instead of Stokes. But the problem is, is similar. You just have an elliptic equation on a perforated domain, and you try to derive such a quantity here. And basically, the idea is again to construct some suitable correctors. So maybe I can give you a hint about the construction for Cioranescu and Murat. So yeah, the idea is that you need somehow to construct some functions. So still in the same setting as there, which will be vanishing on the obstacles or the holes. It would be something which converges to 1 in H1 0 of omega weakly. And for any sequence living in H1 0 of omega, such that it's vanishing on the holes, and such that it's converged strongly to some function, weakly, in H1. Then the product for any test function phi would give you naturally something which would be the analogous of the Brinkman term, but it's rather like a scalar quantity for Laplacian equation for any phi which is a test function, so C infinity of omega. So this basically what you have to remember is that once you have a test function and you multiply it with such a quantity omega epsilon, it will naturally correspond to a test function for the weak formulation of the microscopic system. And since it goes to 1, it's like somehow it doesn't have an impact on the weak formulation, on the starting point, on the nabla u bar epsilon against nabla phi, but it will make appear naturally some strange term. That was the idea in this paper by Cioranescu and Murat. So, and again, such a quantity here is constructed using not the Stokes equation, but the Laplace equation that you will solve on a cell located around one obstacle. Somehow you solve a Laplace equation here, and you prolong it, you extend it, by 1 inside this area here, let's say. And this is how they construct such a quantity. So, these constructions are really, they share some features with the other one, but there are a lot of different things that are called correctors in the literature. So what I would like to show you later for the proof is somehow a self-contained approach using a duality argument which does not rely on some implicit functions here that you have to construct somehow before. Okay, so I just wanted to give you an idea about what has been done in the literature. So let me just maybe continue before switching to slides so that it will be easier to follow. There has been some other results actually. Some other results which actually identify, I think it was the first time where they identify the discrimination of the regimes Brinkman versus Stokes versus Darcy. So Sanchez, Palencia, and this also has been done by Levy almost in the same period. So this is 1982, and this is 1983. So they identify of the regime, the three regimes, so that you either get Stokes at the limit, or Brinkman, or Darcy. And so in the periodic setting, this means that what you have to look at is this famous quantity that I already written before. So either it's converged to some, let's say, constants, so that it gives you Brinkman. Either it's converged to 0. This was somehow already done in the paper by Marchenko and Huslov, because as I said, if R epsilon over epsilon to the power 3 goes to 0, the Brinkman matrix is 0, so that you just recover Stokes. And if this guy goes to infinity, you recover Darcy. And this was somehow the setting considered in the paper by Tartar. And so this paper, I mean, there are some mix between formal arguments and physical considerations, and this has been made more rigorous later. I mean, this the dealing with the three cases has been done in a rigorous way by Haller in 1919, but just before switching to the work by Haller, there has been some other results intermediate that I would like to mention. I mean, all of these deal with the case of periodic distribution. There is also a paper by Briard in 16, which is somehow in the same setting as Marchenko and uses some other approaches. But yeah, I mean, maybe this one I will just skip. I will just talk to finish with this part about the paper by Rubinstein in 1986, which, at my knowledge, is the only one in this period with random distribution of particles. So random distribution of particles. So you assume that your particles are given, distributed according to some law which has some density distribution. And he shows, I mean, this is a mix between some probabilistic method, and approximation of the solution by some point forces. Let me explain this. So basically, this is somehow the idea that I already mentioned yesterday. Sometimes what you can do is, I mean, one step would be to get rid of the physical particles and just replace them by some solutions to Stokes equations with some Dirac mass, which are what we call point forces. So this is but I'm not sure it was completely rigorous for this paper, but the approach for the probabilistic, the random setting was done in this paper, and so they considered the Brinkman regime that I already mentioned yesterday. So because in the random setting you somehow need to prescribe what is the dependence of the radius, which will be different from the one in the periodic setting, plus some other assumptions on the separation between the particles. So the minimal distance between particles. Well, I will not really enter more in that in details, because this we will also discuss in the next minutes. But when you are in maybe a deterministic setting or random distribution like this, what you will see is that we will always need somehow to ensure a well separation between the particles. And the main restrictions would be this. I mean, somehow we would like to reach configuration which are reasonable and physically realizable. So let me switch to the slide. Yes, okay. Yes, so to continue with the historical overview, after that, I mean, there was this famous paper by Haller in 1919 where he identifies these three regimes that I showed to you. I mean, it's written here, right? So this is the formula for general dimension. So if n is equal to 3, we recover somehow what we have done before. So let me maybe explain the link. So this is in a periodic setting, and d is somehow the minimal distance between particles, which corresponds to epsilon in the case of the periodic setting, and r is the diameter or the radius of the particles if they are spherical. So as you can see, for n equals 3, you recover exactly this term. This one. And so he identifies the three regimes so that what you recover at the end is either Stokes, meaning that your particles are too small, or Brinkman, or Darcy, right? And so the formula for the matrix is really similar to the one that I showed to you before. I mean, you just need to solve the Stokes problem on one cell, or thanks to this rescaling here, you can see that this guy will live on a ball with radius epsilon over r, which is big. So that you can approach is actually by the solution on the whole space. What I want, yeah, so let me continue with the literature. And then, I mean, all these results have been done always in the case where the velocity is vanishing on the particles. And then there is this paper by Laurent de Villette, François Goltz, and Valeria Ricci, where they consider the case where the velocity here is not vanishing on the particles. So maybe I would write this more precisely. So you just keep something vanishing on the boundary, but you give yourself some velocities on the ith particle, and this is not in a periodic setting. So the particles are deterministic and they are given. And they assume some separation assumption between the particles. So the minimal distance is at least like n to the power of minus 1/3, which is the setting that you can imagine if you have periodic distribution, because if you have, let's say, n particles here, and you want to fill in a domain which is of volume 1, you see that what you need is that this guy is of order 1. So that you can fill in inside the domain with n particles. So the minimal distance is like 1 over n to the power of 1/3. But actually, this is far from being general. I mean, we know that in general, the particles might have a minimal distance which is really much smaller than 1 over n to the power of 1/3. And so in this result, they somehow need this kinetic energy to be bounded in order to ensure a uniform bound on the velocity. And this I will make precise when I would like, I mean, I will give you a simple proof in this very same setting. So the one where you consider some given velocities, you will see that this kinetic energy naturally pops out in order to ensure uniform bounds on the velocity. And so as you can see, they recover, so they deal also with the nonlinear term of Navier-Stokes, and they recover the Brinkman term. So J here is somehow the analogous of this guy. I mean, if you define Fn as being the empirical measure in both space and velocity, so you get exactly the Brinkman term. And so in this paper, they again use some construction of oscillatory corrections for both the test functions and the solution. So I mean, the idea is always somehow analogous to what has been done in what I have already mentioned before. So then there has been some other results. So for instance, the paper by Feiereisel and co-authors, where they deal with non-spherical particles, I think, and non-periodic, but still with vanishing velocity actually. And they extend to the homogeneous evolutionary Navier-Stokes, which was not done before. And the setting of the minimal distance is quite similar actually to this one. Yeah. And so again, the idea is to use this Stokes capacity like in the paper by Marchenko and Huzlov. And yeah, so I mean, it's basically again the same ingredients that are behind. I would like also to mention this paper by Ofer and Velasquez, where they rather use another method that is the method of reflections. So I mean, this method will deserve a course to itself, but yeah, the idea of this method of reflections is somehow to approach the solution of the Stokes equation on this perforated domain by the superpositions of the solutions of the very same equation, but with one particle at time. So this is, I mean, actually very important, and we will mention it again later on. And there has been some quantitative estimates that I have done with Mathieu Hilleret, and this is more or less what I would like to. I mean, the idea is the one that I would like to present to you. It's based on a duality argument, so that I mean, it's really easier to. I mean, the idea is to avoid this construction, even if there are some similarities. So this is again in the same setting where the minimal distance is like 1 over n to the power of 1/3. And this has been extended by Mathieu, where he was able to do better than a minimal distance of order 1 over n to the power of 1/3. And maybe let me explain this. Okay, we go there. Je sais pas si je dois le rallumer. So the idea is that so you have like many particles, but you don't ask them to be periodic, but you want to ensure that in a cell of length n to the power of -1/3 you don't have only one, but more than one, and you need somehow a uniform control on the number of particles which are in each one of these cells. So this allows you actually to extend the assumption on the minimal distance to something even really smaller than 1 over n to the power of 1/3. So somehow you allow clustering of particles, but you still control their number in each cell. And yeah, so maybe I will quickly finish with this so that I can present to you I mean the proof in a simple setting. There has been also some other results still in not trying to extending the assumption on the minimal distance in order to do something really general. There is this paper by Kleber, Carapatoso, and Mathieu Hilleret where they deal with randomly distributed particles without any assumption on the separation between the particles. So here, I mean, yeah, this is a very general setting. They also include the non-vanishing boundary condition on the particles, and they give quantitative estimates in expectation in this setting. Something has been also done in the case where the particles are given through a Poisson points process, in this paper by Ariana Giunti and Richard Hofer, where they allow overlapping of the particles actually in this paper. And somehow they adapt this, this approach by the construction of oscillating test functions, by somehow canceling what happens in the bad set. So in the sets where there is overlapping of the particles, somehow they prove that you can just, I mean, the construction is quite complex, but you can delete what happens on these bad sets so that it does not have an impact on the limit. So the limit model is, again, the Brinkman term, and this type of overlapping does not have any effects on the limit. There is also another simplified proof in a paper by David Jarre, which is based on another type of corrector functions, for which you need somehow to know the limit model in order to construct suitably your correction to the test functions. And yeah, so there is also results by Mathieu Hilleray, Ayman Moussa, and Frank Sueur, where they deal with the non-spherical case. And they also take into account the rotational effect, which for the moment has been completely neglected in all these results. And somehow they prove that the Brinkman term will also be sensitive to these rotational effects through this resistance matrix that I showed to you yesterday. I also would like to say something about this result by Mathieu Hilleray, which is recent, so in 2021. Actually, in the deterministic setting, what I already mentioned is that the Brinkman setting is the scaling for the Brinkman is this one. But what has considered Mathieu in this paper is the following question: what happens if your radius is smaller? I mean, what do you expect to recover? And so he proves that for any radius which is which is larger, which is larger up to 1 over n to the power of 1/3. So you have like a scaling here. You have 1 over n to the power of 1/3. Here you have Brinkman, and he proves that in this regime, what you recover is Darcy, somehow. And so this is Brinkman. And what is important also in this paper is that he explained that the scaling where the radius is like 1 over n to the power of 1/3 is left open. I mean, this setting is reminiscent of the problem of the effective viscosity, which maybe if I have time, I will explain later. So yeah, this is really an interesting result, which I mean shows that there are still things to do in order to completely understand the scalings around this problem of the Brinkman derivation. So let me just finish quickly with this literature overview. There are also some recent results by Richard Hofer and Jonas Jansen, where they deal with random, identically independent, identically distributed particles, and also velocities, so that they are in these settings, and they prove optimal rates of convergence in this setting. And there is also this paper that I saw recently, the last one, where they deal with non-homogeneous Navier-Stokes. So this somehow closed the literature. I mean, there has been, as you can see, a lot of works on this topic, and there are still things to do. So I know, for instance, that some people are working on trying to derive the Brinkman term starting from, I mean, in the setting of Euler, so for implicit limit. Yeah, so there are lots of open questions still regarding this Brinkman derivation. But mostly what have interested people, as you can see in these, one of these results, was somehow always to extend the assumption on the configuration of the particles so that it is the more general possible. and also to deal with with inertial effects, for instance, also. So maybe I can switch off, unless there are some questions. Yeah, so I will, let me now give you a simple proof in a specific setting. Merci. Je ne sais pas s'il faut tout rallumer. Okay, so I will consider a setting which is similar to the setting of Devillet, Goltz, and Ricci, in the sense that I will include the velocities of the particles to not being vanishing. So let's say UN is VI on the is particle. I will consider balls which are spherical for simplicity. So omega is bounded. And this is 0 on the boundary of the particle, so you have a domain with some particles. So BI is, again, the ball centered in XI with some radius. And I will take quickly the radius being 1/n, which is the Brinkman scaling. And VI are given. Yes, and the particle does not overlap. And I will just, yeah, I mean, you can think of the minimal distance as being something like 1/n to the power of 1/3 at least in this setting. So let me first say something about well-posedness for n fixed, and try to write a weak formulation for this system. Yes, so given for fixed n, we can show that, I mean, we have existence and uniqueness of the velocity, which is h1 of, how do I will call it? Yeah, omega minus the union of the balls. And somehow you can extend UN by the velocity VI inside the particle I. And this is a natural extension, which will be in H10, right, of omega, with a divergence free on omega condition. Okay. We do have a weak formulation. I mean, you can maybe let me just state the theorem. And try to give you a proof. So U bar n is a bounded sequence, actually. so that you can extract a weakly convergent sequence in H1 0, and U solves so the Stokes equation with the Brinkman term. So I will write it like this, like in the setting by De Villet, Goltz, and Ricci. So G is the limit in the sense of measures of this quantity, and rho is the limit of this empirical measure in the sense of measures. Okay. So, yes, sorry, I forgot an assumption on the velocities. This is what I was saying before. So assume that the kinetic energy of these particles are uniformly bounded. And so let me just first give you precise the weak formulation for this system. Maybe I will call it a name. Give it a name, sorry. So you see that if you multiply with something, with the velocity field which is vanishing on the boundary of the particles, for instance. Yeah, so I didn't precise this, but I mean, I will never really speak about the pressure. The pressure, you can think of it as the Lagrange multiplier associated to the divergence free, but so it always exists. I mean, in this omega minus the union of the bars, an associated pressure. But since we will always work with divergence-free functions, it will never appear in the weak formulation. So if you test with, let's say, psi on omega minus the union of the bars, let's say psi is H1 for the moment with divergence free on this set. I should give it a name at some point, but this I can call it omega n. And this is on omega n. So you see, as I said yesterday, this corresponds actually to the divergence of the stress tensor. So maybe I can recall it here. Sigma un Pn is twice the symmetric gradient minus the pressure times the identity in 3 dimensions. So the symmetric gradient is given by this, right? So this is true because if you do the computation, if you compute the divergence of this matrix, you will see that you will have the divergence of the gradient, which is the Laplacian, but the divergence of the symmetric one, I mean, you can perform the integration by parts and use that un is divergence free so that this guy vanishes. So this is how you recover this link here between these two terms. And then you can do an integration by parts so that you get this one, which the derivative which falls over on psi, plus what happens on the boundary, sigma un pn n psi. I will say that psi is vanishing on the boundary of the domain. So that you don't have another term on the boundary. And so as you can see, so this is, so now the idea in order to get a nice weak formulation will be just to set psi to be 0 on the boundary of the particles. So that you get, so let me now make it precise. If you take something which vanishes on both the boundary of the particles and the boundary of the domain, you just have this weak formulation, which comes from this. So maybe I can explain, since this guy is twice the symmetric gradient minus pressure identity. But this is divergence of psi, so it vanishes. And this, due to symmetric consideration of this scalar product, you can always, I mean, from the same reasons, this is the same as this. I mean, you can show that this guy here, after some integration by parts, vanishes. I could also extend all these integrals on the whole omega n if I replace un by u bar n, since anyway the gradient is vanishing. Yeah, but so this is the weak formulation. So basically you will ask for un, so Sn is equivalent to finding some u which is lives in some space that I will call V. So, which is the set of velocities on omega, so that they are divergence free, and they are given by this velocity on the boundary. So that for all psi in, and then I will give a name to this set of velocities, which are defined also on the whole space, and they vanish on the particle. So Sn is equivalent to finding a u bar n in this space, such that for any psi in this space that I will call W, you get gradient u bar and gradient psi is equal to 0. And this you can put omega anyway. Okay. We can also show that we have a variational formulation which will allow us to prove that such a velocity is uniformly bounded. So let me make this more precise. Actually, you can show that this velocity minimizes the energy among all test functions which live in the set V. So one can prove that un or u bar n, I mean, this is the minimizes the energy among V in the space that I have called capital V. And there is an easy way to see this. I mean, if you take such a function V, you can, first, this is the same as this, because they are constants on the particles. And then if you add and subtract un, you will see that you get gradients V minus un gradients un. Right? So you add and subtract un, and you compute this like this. But then you can see that V minus un is in the space W. Where is W? Yes. So V minus un is in W, so that it's a test function for the weak formulation there. So this is 0. So you see that V, the energy of V is larger than always the energy of un unless V is equal to un. So this shows to you that un minimizes such an energy. And then now if you want to show that un is uniformly bounded, the idea is to find a suitable candidate V. Right, so this is less than this for any V in this space. So now the idea is just to find a suitable V so that we can prove that this is uniformly bounded. And in the case of spherical particles, there is an easy construction. The idea is to search for something in V. So V is, what is it? Yeah, so V is the space of divergence-free velocity fields which satisfy being equal to the constant Vi on the ith particle. So the idea is the following one. I mean, we will localize something around each particle and use a simple velocity. So let me write it. So if you look at this guy, x minus xi with the curl. If you do the computation, you can show that, so this is divergence-free because it's the curl of velocity, and this is exactly equal to Vi on the boundary of the particle. And so now if you want something which is only located near the ith particle, I will just make here a cutoff. So let's say x minus xi, located around the ith particle. So key will be 0 or 1 in the ball centered in 0 with some radius, something a little bit larger than 1, let's say 4/3, and 0 outside of the ball of radius 2. So this means that I'm constructing, so let me call this Vi. So Vi lives on the ball
Vi is h10 in the ball centered in xi with twice the radius. So this is the radius, this is twice the radius. So it's equal to Vi locally on the particle, and then it decreases and vanishes outside this ball. So the advantage of this is that now I can sum such VIs on all the particles, and I will naturally have something which is divergence free and satisfies being equal to Vi on each one of the particles. So let me call this V or Vn, I don't know. Okay. So this is in V. Maybe there are some questions. And so now what we will do is just, I mean, you need to have an idea about the energy of such a guy in order to get a bound for the velocity. So what you can see is that Vi is basically like, I mean, you have one derivative here which will fall either on this guy, so it gives you either something proportional to Vi up to a constant, or, I mean, the derivative might fall on the smooth function here, the cutoff, so that it will bring you 1 over r, right? But since here you are looking at something near its particle, this is of length r, so that you get the r compensated and you get just Vi. I mean, you can write this like this, right? But so for the energy, what we want is the gradient of Vi, right? So maybe let me write this. So either Vi times k, or either one derivative falling on k, the cutoff. With x minus xi. So now if I derive another time, you can see that this guy will bring you 1 over r. Either it falls on this, or either it falls on this. So basically, yeah, I mean, this is the worst. Yes, sir. So that they are both, yes, they are both scaling like this. So now if you look at the energy of such a guy, so you get Vi square, the volume, which is r to the power 3 divided by r square. Sorry, r. Right. Okay, let me. So I will just bound it by this. Okay, the volume. But this is like R3, so that you get R Vi squared. And so, so you see now, if I want the energy of V, I will just sum over these non-overlapping. I mean, the VI's live on. I mean, the support of each VI is does not overlap with the other VJs. So the support of VI So for this, I need to assume a little bit then this assumption. I mean, I need a little bit more so that the balls of radius 2r do not overlap. Okay. And so the energy of V is like omega, but this is like a sum of Vi square R constants, right? Because of and so you see if R is like 1 over n, yeah.
The bound would be okay even if they overlap. Here's the upper bound.
Which one overlap? The balls of radius R? You're asking?
Just to be sure, you said that you need here that you use the assumption that they do not overlap.
I need a little bit more. Yeah. I mean, I need the ball of center 2R does not overlap. So I need the minimal distance to be larger than 4R.
Where do you use it exactly?
I mean, I am using that the energy of V is like the sum of the energies of Vi, which has disjoint support. So yeah, if they overlap, you might have...
What I mean is that it's not sharp, but you could write it in any case.
If the minimal distance is larger than 4R. Yes. And so sorry, I switch between R and 1 over n. So R is 1 over n. So that you see that this guy is exactly the kinetic energy. So this is the assumption needed, which was there in the theorem. So this is bounded. So now R is like 1 over n. So this will be bounded. Okay, so all of this just shows you that U bar n is uniformly bounded in H10. Because Un is uniformly bounded, and if you extend by the velocities Vi, you will get some similar, bound. If you look at the energy of U bar n. No, sorry, no, it's the same. I was thinking about the L2, no, sorry. Yeah, so this is the same energy. Okay. So now we know that U bar n up to a sequence will converge, up to a subsequence will converge to some density, to some function which will be in H10 of omega. Okay. Now the question is, what is the equation satisfied by U? And so as I said before, the idea is that if you take a test function, so let psi be sin infinity divergence free. So I want a test function which does not see the particles anymore, right, in the limit. And I want to say something about this quantity. And if I know a formula for this quantity, this will give me a weak formulation for the limit system. But this is just the limit of gradient Un, right, or U bar n. So we are tempted to use the weak formulation for Un, but this is not in the right space. Right? Psi is not in W. But so the idea is that let me multiply the equation Sn by such a test function. So multiplying Sn by such a psi, we get what? So it's exactly the computation that I did before, but yeah, so let me go a little bit faster. So this is minus gradients un, gradients psi on omega n plus the sum of the un pn psi. So this is exactly the same computations as before. But so now psi is not vanishing on the boundary, right? So this tells you that this guy is this one, right? And so as you can see, the only information that I need to know about psi is its value on the boundary. So that's actually, if I replace here psi by any other test function which has the same value as psi on the boundary, well, this doesn't change anything, right? So the idea is to introduce some suitable test function which will replace this one. So the only value that matters, as I said, is the value of psi on the boundaries, right? So the idea is to introduce some function that I will call psi bar n, which solves the Stokes equation near each particle. So let's put this on a ball around the east particle. So I will take a ball of radius the minimal distance over 2, so that, again, these will not overlap. And I will just ask psi bar I to be psi on the boundary of the particle. So this is bi. And psi bar I is 0 on the boundary of the external particle. So let me make a picture. So you have your particles. D is the minimal distance between them. So if I focus on a ball of the radius minimal distance over 2, I will get some non-overlapping balls. And I will try to solve a Stokes equation on each one of these annulus. Okay. And the only thing is, the idea will be to replace this psi by this psi bar I, because they both have the same value. And this is the only thing that matters in this weak formulation. Right. So I can say that gradient un, gradient psi, is the sum of sigma psi, which is also the same as psi bar I, because they have the same value. And then I can go a step further in the simplification of this psi bar I. Again, since the particle is small, I will just replace psi by its value in the center. And this will lead an error, but we can prove that such an error is small. Okay, I will not prove that the errors are small. I will just try to convince you how to make appear the Brinkman term. So we will replace psi bar I by, let's call it psi tilde, because there will be another one later, solving the very same Stokes equation on the annulus. So let me give this a name. This is AI. So that I don't have to write it again. Divergence
is 0, and psi tilde is psi of xi. So it's a constant on the boundary of the if particle, and it's 0 outside of the annulus, so the boundary of xi d over 2. And so now is to perform just an integration by parts. So on the term, which is there. So gradient un, gradient psi is this guy. Which is almost this guy up to an error. Which we can prove that it's small. And then now we can do an integration by parts. So this you can show that it's, so either the derivative falls on the sigma, so it gives you just the Stokes equation, which is vanishing. Either it falls on the psi tilde, right? So again, it will give you this. But since psi tilde I is supported on in this annulus here, or in the ball, I mean, I can extend this by, I can extend it by 0 outside of the ball of center xi and the radius d over 2. So, I mean, this is exactly this. But then you need to sum, right, on the particles. And so again, sigma is just the gradient of un. And then the trick is that now, since psi tilde I also solves the Stokes equation, I can do an integration by parts in the reverse sense. So I can now make appear not the stress tensor of un, but I will make appear the stress tensor of psi tilde I. Okay, so I will do again an integration by parts using that psi tilde I solves this Stokes equation. And so I have to be careful about the signs, but there is no minus, right? Yeah, there is no minus here, right? And so now, if I do an integration by parts, so this I can write it again as the divergence of sigma of psi tilde with a pi tilde, which would be the associated pressure. So that what you get is this. So either, I can also even switch to this since un is vanishing on the particle, right? So I either get a boundary term on the exterior ball of this sigma psi tilde, or on the particle bi. And now I have to be careful about the normal. So I'm integrating on this annulus so that the normal is pointing outside of the domain. So if I may call, if I use just the normal which points always outside of the particle, this should be a minus, right? On the and so we are almost done actually.
Okay, I just have 5 minutes. UN is constant on the ball. So this is VI. And now the trick is that this psi tilde I, again, is almost the same as solving the same Stokes equation, but on the whole space minus the ball. Because the ratio between this distance here, which is the radius, and this distance here, which is the minimal distance, so this goes to 0, or vice versa. D over R goes to infinity, so that we can replace the force. I mean, this is the drag force associated to this flow, right? The force applied by the fluid on such a particle. So the idea is that this guy is almost like the drag force associated to these specific solutions that we saw yesterday, which was given by 6 pi r times the constant on the boundary. So this is the idea. So it's really, I mean, maybe a little bit more computation that constructing some correctors, but I mean, it's really just using a duality argument in order to, so this guy here is almost like, I mean, this we can prove, actually, we can compute this. Let me call it psi, where psi solves the same equation, but on the whole space minus the ball. Divergence psi is 0. So it has the same value as psi tilde on the boundary, and it vanishes. But this we know, I mean, from yesterday, this was 6pr times the constant here. And I just have to be careful about the normal. So if it points inside, there should be a plus, otherwise it's a minus, but nevertheless, right? So this tells you that this guy is like 6pr psi xi times vi. And this makes already appear one of the terms for the Brinkman. And for the other one, the idea is that, again, since you are working always on some balls which have a small radius, the idea is that UN I can approach it by its mean value around this annulus. This makes another error, but we can show that it's small. And the advantage is that if UN was constant, we will again get here the drag force, because this integrated over the outside ball is the same as integrated against on the inside ball, right? Because it's divergence free. I mean, this sigma is divergence free on the annulus. So you get to conclude. And I hope I will finish this. I don't know how much time can I come here. So let me write again this. So I said that's the last part. So the last part is, so n is the outer normal, and this is the inner, so there should be a plus r vi psi xi. Okay. I don't know if it's clear. Okay, so now for the other term, you can see that the idea is to approach un by its mean value, which will generate another error, but we can prove that it's small. So let me replace un by its value on AI, or maybe, okay, it's not really AI, but let's say it's this value that I will take, so that this goes out from the integral, and then we can show that, so integrating on the outside bar, sigma, after an integration by parts, you can see that this is like integrating on the inside, right, particle, because sigma is divergence free in the annulus, because sigma of the divergence is just the Stokes equation, which is up to some maybe different normals and different signs. There should be a minus again, and these points outside of the particle, no, sorry. Yeah, so you do an integration by parts on this annulus, so you get the normals which are outside of this annulus, right? But so you know that this one is 6PR psi, right? This is what we already used before. So that this again is like 6PR psi times the mean value of un. And then you just, let me conclude quickly, or maybe we can discuss about this tomorrow. No, sorry, not tomorrow, Thursday. So at the end, what you get is some 6PR VI times either psi or this one, which is a mean value of un. And then, okay, so since I don't have time, I will just give you a formal argument. If you assume that un is close to a limit quantity, we know that un converges weakly in H1, so it converges strongly in L2. This you can replace somehow by u in xi. This is formal. And so that you know that, and so that you see that this is basically the Brinkman term. R is like 1 over n. So what you have here is 6p v minus u integrated against psi fn, right? And fn is this empirical measure that I already introduced yesterday. So under the assumptions, and yeah, these are also forgot. In the theorem, you need to assume, no, it's written. So these two measures are basically the ones which appear here and here, right? So we assume that v fn converges to j, and rho n, which will be the density, the spatial density, converges to some rho, so that here you make appear the Brinkman term. Okay. I will stop here. If there is some questions, I would be happy to answer.
Are there any questions?
I have a small one. So where did you use the 1 to n to the 1/3 condition?
In the error terms that I didn't. You need somehow to ensure that your particles are far away, so that these interactions are not too big. But actually, such an approach has been extended by Mathieu for a setting where the minimal distance is even smaller. So it works in the same spirit. So this very same duality argument works for worst minimal distance.
And so I don't remember, but the original proof of the Villette-Goss-Ricci is not this one.
No,
Right.
no. So they introduced this type of correctors for both the test function and the solutions, and yeah.
I have also a question/remark, which is more on a technical point. I don't think it would change much, but maybe in the precise case in which you are, in which UN is constant on the boundary of the balls, I would expect to have some kind of orthogonality, and it would be maybe more natural to replace the value of psi with a bar instead of the value at the center with the average on the sphere. And then you won't have any error terms because you know that UN is constant on the boundary. What I expect is that you have at some point in your computation an integral on the boundary which relates U, which is constant, in front of some test function.
Yeah.
And then you decide to replace the value of this function by the value in the center.
Yes.
And you say that it's okay, we'll have some error terms. Maybe you can even get rid of them if you just use the average on the sphere.
For which one? For psi? You mean you replace this one by the average?
Instead, yes, just like you do then for U, you would do the same thing for the test function, but using the average on the sphere.
But this will, and you think this will not generate an error? I mean, here you will take.
So I did not write the computation, but what I expected, you know, when you integrate some function which has zero average in front of a constant, then you get zero. And this is just what I'm saying. So I'm wondering how much, because this is more natural to replace it by its average where you integrate instead of its value in the center.
Yeah, I mean, I think that you will get some. I mean, if you look at sigma of UN psi minus its average, let's say, on the ball, I don't think that this is zero. I mean, if you do an integration by parts, I mean, if you look at the lifting of this guy on the annulus,
I would average on the sphere, not the ball. But
okay.
Okay, you're not sure that it's vanishing. I don't know. Anyway, at the end, you'll have to, since you want the Dirac mass, you'll have to replace this average by the value in the center. As I told you, it's more a remark than a question.
Okay. Yeah. Thanks.